For this introduction. I'd like to thank the organizers for giving me a chance to present this work. Here, I really enjoyed the conference. Just one disclaimer up front, I really lost a fight with jet lag, and I slept on average like less than 5 hours a day in the last 4 days. So yeah, I might be a bit down today, but let's try. Right, and right, so I should, it works. Yeah, I should say that this is joint work together with Marco Rubio from INL, Leonardo Novo, his PhD advisor, also from INL, Ernesto, now Uf, previously INL in Braga, and Nicola Serf, and yeah, it's done within those 2 projects. So EPIC, I guess Iris is also an EPIC project, and Tukan, Daniel mentioned it in the first day. Right, so I'll be talking about in the partial distinguishability and indistinguishability of photons. So I was actually very much like puzzled by this topic for many years, and I think with this project I managed to like get better understanding. But okay, I tried to convey it to you, but I slept just 4 hours today, so let's see. Maybe it will be the opposite. Right, so yeah, so just when we look on bosonic particles, you know, due to symmetrization, we cannot like distinguish. Oh, what I did. Oh, we cannot distinguish in which state particles are in first quantization, because yeah, we have to symmetrize the wave function. But it works or not? Oh, sorry. There is this delay. Okay. Right. Yeah, I need to adjust. Right, but when bosons have like external degrees of freedom, say position, you can distinguish them, because okay, sorry, I guess you can distinguish them because yeah, let's say this particle is actually in the the left part of the screen, this in the right part. So when you you know, you have those like external degrees of freedom that allow you to distinguish them, and like something can be in internal degrees of freedom. And okay, like when you now measure such a state using detectors that are sensitive to which part of the space you are at, this state behaves as if you had this, just distinguishable particles, just product of psi and phi. Okay, yeah, so that's why when we have like 2 electrons like here and like at the moon, like we can like talk of them about as distinguishable particles. Okay, but for many applications, it is desirable that, you know, in those internal degrees of freedom, like spin, polarization, like think like states are like the same. Okay, so then like external degrees of freedom behave like bosonic ones, so you symmetrize. And yeah, what are those like applications where this arises? So when you do yeah, quantum metrology and your photons are distinguishable, you use Heisenberg scaling. Also, you use hardness in quantum advantage experiments. And also, okay, whenever actually you have, yeah, like, okay, there are some optical incarnations of quantum computing, like KLM, measurement-based quantum computation. Like, if you don't have, if your photons are not indistinguishable, then you lose like the magic, let's say. And this is like because like some things you can do due to this entanglement in particles that arises if they are really indistinguishable. Yeah, also in communication it arises. Right. So this talk is about scalable and fairly easy to implement method for certification of n-photon indistinguishability of photonic states that come, let's say, from n sources. So I'm imagining the scenario when I have like n ports and some photonic state comes in, and I wonder whether it's distinguishable or whether it's indistinguishable or not. Okay, so now some theory, of partial distinguishability. So on the level of a single particle, I have I postulate that Hilbert space is a tensor product of some external degrees of freedom and internal degrees of freedom. External are the ones that I can address. Internal are the ones to which I don't have access, like let's say frequency or polarization in some setups. Right, and there will be like some game between external and internal degrees of freedom throughout the talk. So mostly external degrees of freedom would be denoted in black, internal by red, and like if there's mixture of both, like in blue. Let's see if we can come up, if we can keep up with that. Right, and now when you have multipartite bosonic Hilbert space, which is just like symmetrization of the single particle Hilbert space, n-fold symmetrization. But you can like equivalently describe this this problem in a second quantization, and the tension comes from the fact that many things are actually nice and easy in first quantization, but physicists they are not used to first quantization, so it's a bit of a tension. Let's see and so I'll be going back and forth a bit between the two. So I will be especially interested in states that enter in the first n modes of my system. Okay, they have a definite photon number 1 in first, second, up to n optical mode. And then imagine I have some internal states alpha 1, alpha 2, up to alpha n in those states. I can now just create those particles from bosonic vacuum. Right, so I have this external index I, internal index alpha. Right, and there is one basic, but for me very crucial and illuminating observation, is that this class of states, actually this is like, you can regard them as just image of some isometry. So, that takes you from n copies of indistinguishable particles to this bosonic Hilbert space. So those alpha I, they just behave like just basis states, and you map it into this string of alphas. And then when you check like inner products, like it's preserved. So you can regard like that, such a just product of many indistinguishable particles is just embedded into bosonic space like this via this isometry. Okay, and so it's geometry. It doesn't matter if you look on bosons or you look on internal degrees of freedom. So I'll be, throughout the rest of the talk, image of this embedding I will denote by omega. And it's going to be very, I can have product states here, separable states, entangled states, okay? So this allows me to treat them at the same footing. And most of other approaches, maybe with the exception of this last work by Engelbrecht, sort of focuses on like very specific scenarios where those states row are maybe like, just product, for example, across like here. Okay, so this is, okay, it's not so bad with time, good. Okay, so now let us meditate a bit on like, in this language, what it would mean for me to have perfectly indistinguishable photons or bosons. So, imagine the scenario when I'm not looking on those internal degrees of freedom at all. So I want that for all practical purposes, like if I forget about those internal degrees of freedom, I'll be left with a state that describes a system of perfectly indistinguishable bosons. Okay, So that makes sense, right? So for all experiments that I do on external degrees of freedom, whatever I do behaves as if I had perfectly indistinguishable bosons, photons in this specific state, like standard Fock state. Okay, so this is for me, like a definition of being perfectly indistinguishable. Right, yeah, and one can formalize it, so just sort of demand that, yeah, like the reduction of the state omega to those external degrees of freedom is exactly this Fock state. Good, I can postulate something like this. And now, using language of first quantization, I can write some formula for this reduction. Okay, it's like a double sum of permutations. It's complicated. Right, so maybe, yeah, what I should say is that this just the external part of my state, so what experimentalists see, is just like some specific state on just many like tensor product of external degrees of freedom. It's not necessarily symmetric. And some things to note is that it depends on exponentially many number of parameters. Those parameters, I mean those. Okay, what is happening here is that I have this row. Okay, this row is sort of, I take expectation value of some permutation operator here that permutes factors of those internal degrees of freedom. So I have those crazy quantities. They are not directly accessible. Moreover, I have, when I just rotate my internal degrees of freedom by many copies of U, my external state remains the same. So those are like challenges I need to face. And now, what I can do, just to maybe make my life a bit easier, is that there is some constant missing here. So when you look at this, you actually realize that you recover this Fock state n0 if and only if those contractions are all equal to 1. So what this means is that rho is an like eigenstate or like eigenoperator of of every permutation with eigenvalue 1, which means that support of rho is in the symmetric subspace of those internal degrees of freedom. Okay, so what is here? I forgot 1 over n factorial. Sorry for that. I have a fact that this photonic state of many particles is perfectly indistinguishable if and only if its internal part, is fully symmetric. Okay, some mathematical characterization for now. Okay, so I see. Yeah, let us move further. So now I don't want to just say what it means. So what it means to be perfectly indistinguishable, but maybe I want to be approximately indistinguishable. So we decided to look on fidelity. So we want to find a state, which is, I have my state omega of rho here, and I want to assess how close is it to the state of perfectly indistinguishable bosons. Yeah, we decide to look on fidelity, Ullmann fidelity. Great. Yeah, looks complicated for now. Right, but actually one can prove funny thing that expectation value of rho on this symmetric projector actually measures for you the fidelity to the closest indistinguishable state. So this is really a very good measure of this indistinguishability. Okay, one can solve this optimization problem explicitly. Moreover, one can also prove that reduced state is just has a fraction of the state n0, which is proportional to this fidelity, and proportionality constant is this fidelity, and some junk which is orthogonal to it. Okay, so we get now that the trace distance, so bona fide distinguishability measure between the reduced state on external degrees of freedom that we care about and Fock state that we care about is just given in terms of this fidelity, 1 minus this fidelity, and yeah, closeness in this trace distance implies that all experiments that I perform would have close statistics in TV distance. Good. So this is, I want to argue, is a good indicator of closeness. Now, we would like to maybe measure those things, right? Like sort of, I mean, okay, there is some math involved and some internal, external degrees of freedom, but I want to have something measurable that I can hopefully maybe implement in laboratory, or not me, or maybe my experimental colleagues. Yeah, me definitely not. Okay, so let's take a step back, and okay, let's look. Okay, let's consider specific permutation of internal degrees of freedom, cycles. Okay, some cycle that goes over all my particles. And now I can consider, it acts on internal degrees of freedom, and I can look on the projector onto, defines a group, cyclic group. I can look on the projector onto this trivial representation. And some basic observation that one can have is that this row, if this row is product, actually being fully symmetric means that it's if and only if you are symmetric just over cycles. So let's develop this observation further, and it's our first result. So okay, recall that this fidelity to the closest indistinguishable state is given by this by this projector, expectation value of this projector. And now let's look on projector onto this cyclic trivial cyclic space. Okay, then for product states we have the following. So product states means independent sources physically. We have two-sided bounds on this fidelity. Okay, with this expectation value. So and furthermore, this number itself we can estimate efficiently by just a single interferometer, namely Fourier transform that, for example, Ernesto was talking about. Right, and simple post-processing. So what happens geometrically is that I have my set of fully indistinguishable states, and this criterion gives me upper and lower bounds, two-sided bounds on this fidelity that are fairly, let's say, tight. Okay. And sample complexity of estimating this guy just grows to additive accuracy is just 1/epsilon². Doesn't depend on the number of particles. Okay, so it's one test one circuit you run and repeat many times post process. Okay, I see. And one comment is that those cyclic permutations, as Ernesto mentioned last time, they give rise to Bargman invariants, okay, that we analyzed in earlier works with Ernesto. What I have then? I have the second result. Yeah, so one can wonder, okay, but what if my state is not product? Okay, so I can have correlations between sources. I can have entanglement, like Candela has entangled source entanglement in internal degrees of freedom. So what then? So the thing is, you can still estimate this fidelity efficiently by just doing randomized linear optical circuits and particle number detectors. And I should say that independently of our work, there are two works that use cyclic interferometers to just from this year to argue about indistinguishability of specific classes of states here. Good comparison with previous approaches. Yeah, so very quickly. Ernesto told you all about this on Tuesday, I believe. So, Hongo-Mendel test give you a way to assess pairwise overlaps between states. Those things were later generalized. Okay, people studied this triad phase in the three-dimensional quantum Fourier transform interferometer, and you had some information there about this third order invariant, the pairwise overlaps. For specific model of input states, people that Daniel and Ernesto, I think, introduced, like when your states are diagonal in a fixed basis, like people studied indistinguishability also for moderate size systems, and people like, again, Daniel and Ernesto and Fabio. And just recently from Fabio group, there was like some nice PRX paper that estimated Bargmann, but invariant of high degree, but with it's with exponential overhead with number of particles. So this is the context. Yeah, I think I have like 5 more minutes, right? So it's fine. Yeah, so this is maybe one thing I'll be spending a bit more time on. Right, so how you measure those cycle? Yeah, so what we do, like to have those claims, like we actually measure cyclic invariances. Yeah, and there is some nice mathematical reason for that. So yeah, let's ignore the figure. Let's look on the picture. So let pi be some optical transformation that permutes my external modes according to some permutation. Okay, so yeah, it permutes my modes. Okay, and then first n modes. So then what sort of happens is that if I act on this encoded complicated state with this permutation, what I'm getting as a result is, you know, I can sort of effectively implement this permutation on internal degrees of freedom. Okay, yeah, the same permutation. That's now, you know, regardless if my state is product or not, it's gonna just swap my particles around. And like when you use this, you'll get that to compute expectation value of some permutation operator on internal degrees of freedom, it's enough to compute expectation value of this permutation on external degrees of freedom. I know it's a bit crazy, like you have internal and external degrees of freedom, but this is something that you can perhaps measure. So how you measure this? Okay, so you like this transformation is diagonal in some basis, so that's VB diagonalization transformation, linear optical. And then one can just convince yourself that this expectation value just amounts, okay, ignore the formula, look on the figure. You can get access to this expectation value by having this input state, applying the inverse of V that appears here, doing particle number measurement, and then you post-process according to spectrum of D. So you can do it easily with linear optics. So this allows you to measure specific permutations, project onto the cycle, in particular, okay, Bargmann projection onto this EREP via, in this case, is via Fourier transform, because this V is essentially Fourier transform. And Ernesto and my co-authors had a paper just about measuring, let's say, those Bargmanns recently. Okay. Now, I think I'm like running out of time a bit. So just maybe to give you like intuition why our criteria works. So, right, okay, okay, so I have this one specific Bargmann invariant, but let's look also on other Bargmann invariants that come from the cycle, like applying higher cycles, okay, like powers of C. Okay, and let's just assume for now that, yeah, like we know that magnitudes of those cycles, those Bargmann invariants are large. So we can prove some fairly simple bounds that say that like just product of like fidelities that appear of neighboring states in this cycle is like lower bounded by its value. And also we can put lower bound on product of fidelities to pure states, okay? That are closest to rho I, okay? So when you combine this, qualitatively you get that large values of all those invariants, magnitudes of all those invariants, imply that this product state is close to product pure state, okay? Because yeah, when you combine all of them. So this is on the qualitative level. To get, I just skip for the sake of time. You need to be a bit ingenious to get the bounds that we have. Okay, I just skip this. Right, so summary. Yeah, I talked about certification of sources coming up from of photonic states that come from n sources. Okay, so they have definite occupation numbers like this. And first, say qualitative result is some explicit formula about the fidelity to the closest indistinguishable state. Yeah, in terms of like projector onto symmetric subspace of internal degrees of freedom. And we have sample and computationally efficient methods to either bound or estimate this fidelity to additive distance, to additive precision. And in the future, we'd like to analyze subroughness to imperfections of that, maybe do experimental demonstrations. Okay. There is some nice mathematics in this game that I hidden under the hood. So yeah, for example, it would be nice to have like shadow tomography protocol for those internal degrees of freedom. And I think there is some room to explore when it comes to application of partial distinguishability in quantum advantage schemes and like other quantum algorithms because of this mathematics. And okay, just some advertisement at the very end. We are very happy in my institute in Warsaw recently to get a big grant for a quantum excellence center in like quantum-enabled computing. The head is Michał Gusiak, I'm group leader, and Michał Matuszewski, who does polarity on physics, is also group leader. And some like couple of announcements. We very soon we're gonna have calls for 2 group leaders for roughly 3.5 years, some nice salary, nice seed money, so postdocs, some PhD students, travel money, and there will be plenty of calls for postdocs, students, etc. So if you are interested or you know somebody who is, contact me or Amik. Yeah, thank you for your attention. Okay, so you measure it basically by measuring permutations, okay? And the basic trick is is this. You can measure, so you have some mathematical identity that allows you to measure expectation value on the permutation on internal degrees of freedom by measuring expectation value of some permutation of modes, which is something you can implement with linear optics. And then what you do, you decompose this linear optical transformation into like basis that diagonalizes it, and you basically do you implement V or V dagger and some post processing. Like you combine the results later. Yeah. Thanks.